Alright, today we will do delay differential equations, and these are a special case of functional differential equations. So let me first remind you about ordinary differential equations, which is what we have spent a lot of time doing in this course, and that is something like this. X dot is equal to f of x t. What this means, I'm using a scalar analogy here. This can actually be a vector system, but the scalar picture is like this. This is t, this is x. You have an evolving solution. At some time, this x has some value, right? And the slope here, this slope is x dot, and it depends explicitly on this time and on this x. The past values have contributed to the evolution and determined which point you will reach, but the further evolution from this point depend only on this initial value or initial condition. Clear, I hope. Now when you come to a DDE, so here is a simple example. X dot is equal to minus x, but x dot at t is equal to minus x at t minus x at t minus 0.4. So you see, this is a peculiar equation because it depends, the rate of change at time t depends on a past value. Okay, so let us depict this pictorially. So what it means is, this is the DDE example. So what it means is, if this is x and this is t and we've somehow come somewhere, so let's say that's our point of interest t, and let us say this gap is 0.4, right? So if we say x dot at t is some function of x at t, x at t minus 0.4 as well as t, explicitly it depends on all three things. In that case, the slope here, this slope depends on this t, this value of x, as well as this delayed value of x. So it explicitly depends on that. And this really makes a big difference, because now when I march forward a little, let us say from here I've come here and I have to get a new slope, so I have to come to this point and march forward by an equal amount, and once again I need that 0.4 delay, and I need to know this height in order to compute this slope. And so the initial condition for this dynamical system is actually a function on an interval of length 4. Okay, so that's the first thing to notice. That is why it is infinite dimensional, because the initial condition is not a point, it is a function. So you need an initial function. This is one important point. Of course, you can have more than one delay. So a general situation for something called a retarded functional differential equation, RFDE, is x dot at t is equal to some function of x at t minus tau 1, x at t minus tau 2, x at t minus tau n, and t explicitly. Okay, so there are delays. Tau 1 is less than tau 2 is less than tau 3 is less than tau n, and we will assume that the delay is finite. Okay, so in this case the maximum delay is tau n, and the initial function must be given on an interval of length tau n. Okay, and once we know this initial function, then in principle we can integrate forward using some numerical method of our choice. All right. You can also have a situation where you could have x dot of t is some function of x of t minus tau 1, x of t minus tau n. So all these delayed variables, there's that, but also x dot at t minus tau 1, x dot at t minus tau 2, and so on, t minus tau n, and then the t itself. So this is actually more complicated. Remember, this can be a vector system in first order form. So what we are really saying is that in this case, these are called neutral delay differential equations. So in neutral delay differential equations, what happens is that the highest order derivative also is delayed. Okay, so the highest order derivative at the time of interest depends on delayed values of that highest order derivative. So these are harder. We are not going to talk about this, but if you think about it further, you will see why they are more difficult. Let us look at the simplest case possible, which is the linear constant coefficient scalar case, and I will use second order so that you will see why or how it generalizes, but first order is sufficiently interesting for our case, for our purposes in this course. But let me write it like this. So let me say x double dot at time t plus c1 x dot at time t plus c2 x dot at time t minus some. Let me just use delta as a delay, and I'll use only a single delay, plus k1 x at t plus k2 x at t minus delta equals 0. Okay, so well, this is, first order would be simpler than that, but this is the scalar case, and the simplicity lies in the fact that it is linear, it is constant coefficient, it is scalar. Okay, the second order derivative introduces relatively less conceptual complication, as you will see. All right, how do we proceed? We seek solutions of the form e to the power lambda t. Linear constant coefficient systems have solutions like that, but when we substitute it in here, what we get is lambda square e to the lambda t plus c1 lambda e to the lambda t plus c2 lambda e to the power lambda t minus delta plus k1 e to the lambda t plus k2 e to the lambda t minus delta equals 0. Okay, and of course, as you are fully familiar with this idea, e to the lambda t is not equal to 0, so we will cancel that, and when we cancel that, then we get this very interesting characteristic equation. Let me write it in green here. So what we will get is lambda square plus c1 lambda, so we will get lambda square plus c1 lambda plus c2 lambda e to the power minus lambda delta plus k1 plus k2 e to the power minus lambda delta equals 0. So this is the characteristic equation, and some of you may be familiar with this idea that since this is a transcendental equation, it actually has infinitely many roots. Okay, so it is infinitely many roots. What we will find soon is that most of those roots for delta is greater than 0 by assumption. You don't want a situation where delta is negative, because that is not good for forward dynamics. The evolution of the present state would then depend on the future state, which is not yet known. In some funny situation, you may end up with an equation like that, but when you are talking about dynamics and solving initial value problems, you will not have that, because you violate causality where the future determines the present. Okay, so this has infinitely many roots, and we will have to think about what those roots are like. And so to think about what those roots are like, we will come here and do the simplest, simplest with 2 exclamation marks, simplest case. X dot at t is equal to minus a x at t minus 1. How about that? Can't get simpler than that. Okay, so now this one, our characteristic equation is lambda is equal to minus a e to the power minus lambda, or lambda plus a e to the power minus lambda equals 0. Okay, a can be positive or negative, doesn't matter. Now we will have to say something, we will have to know, whether any lambda has a positive real part. If it does, then the system is unstable. There is exponential growth. Okay, but it could also be, that all lambdas have negative real parts, in which case we will have stable. Okay, now you can think about this in the following way. Suppose I have x dot is equal to minus ax at t minus 1, and I think of a greater than 0, but I think of a much less than 1. So x dot is almost 0 if x of t minus 1 is not very big. So let us think of moderate rates of change. Okay, when I think of moderate rates of change, what do I mean? This is not very big, then x of t minus 1 is not very different from x, and then this a is there and a is small, and this means that x dot is sort of small. So once that happens, then x at t minus 1 is not very different from x. And so you see, for small a, 1 lambda solution is about minus a. Okay, so here lambda equals minus a e to the power minus lambda. If a is very small, then e to the minus lambda is close to 1, and then lambda is minus a. But what about other roots. If we have infinitely many roots, then they cannot be in a bounded region of the complex plane, right? So why? Because if you have infinitely many points in a bounded region, then there has to be some tiny little circle inside which there are infinitely many points. That's called an accumulation point. There has to be such a point. When you look at that point, then you realize this is an analytic function, right? This is an analytic function. This thing here, it's an entire function. In fact, its Taylor series converges everywhere on the complex plane. But if you pose a Taylor series about that point, because there are infinitely many zeros, infinitely many derivatives are zero, and so the function would have to be identically zero. But the function is not identically zero because there are some values of lambda for which it is not zero. This gives you a contradiction. So if there are infinitely many roots, they cannot be in a bounded region. So if there are infinitely many roots, the roots themselves have to be unbounded. So no matter how big you take real part of lambda, imaginary part of lambda, you take a big region, and it doesn't matter how big this region is, there are roots outside it. Okay, but where are those roots? To understand where those roots are, if lambda is very big, then one way or another the rate of change of x is very big, right? Because that is proportional to lambda. So now if this is very big, what we are getting here is that if lambda is very big in magnitude, then lambda e to the power lambda, which is minus a, still has to be small. And this means that e to the power minus lambda is very small. And what this means, wait a second, e to the power plus lambda is very small. And what this means is that if there are large roots of this equation, those large roots have negative real parts. And why do they have negative real parts? That is because, remember, there was actually a lambda delta here, and delta is 1. If the delay was negative, that means you are seeing the future, then you would have infinitely many roots with very large positive real parts. So in such cases, future prediction is not possible. Okay? Let me point out something else about these equations that is very interesting, and that will be the end of this impromptu lecture. Sorry, this informal lecture. So here is this interesting thing. Let us say x dot is a function of x dot at t is a function of x at t, x at t minus 1, etc. Something. Let's just say that. So now let's say the initial function is like this. Let us say the initial function is discontinuous. Okay, so this is t equals 0, this is t equals minus 1, this is our initial function. So there is a discontinuity. In this case, this is proceeding as it is. This one has a discontinuity when I reach this point in time. That means x dot has a discontinuity, which means that over here I'll have a slope discontinuity. Then when I march forward again from t equals 1 to t equals 2, x at t minus 1 will have a slope discontinuity. Therefore, x dot will have a slope discontinuity, which means that x will have a curvature discontinuity. In this way, with every delay interval that passes, the solution becomes smoother, which is rather nice. Okay, so one more thing is, I will not go into the formal aspects of the matter, But if you read books on delay differential equations, you will find that they take this interval as an important part of their theory, and they think of this function being mapped to some function, being mapped to some function. That is how some people think about it, and it is useful when you want to develop theory. But we are interested in understanding roughly how it works, numerical solutions, and some analytical treatment. So we will continue in the next lecture.